Okay, everybody, we're going to take a look at a new method of integration. It's called integration by separable differential equations. We now have been practicing integration by use substitution. So when we have functions inside of other functions and when just simple anti-differentiation doesn't work. So now we're going to see this other technique, and we'll show you in a second of where this is used and how you can easily spot when you're going to use this technique. You need your notebook. So make sure you got your notebook ready. You're going to do some examples with me. Try to get you to do some. And remember, you can always pause me if you want to try one on your own, or when I ask you to pause and then give a problem a try. Be sure to see that there's going to be other example practice problems on the lesson page as well. So let's get right in. So 6.2 integration by separable differential equations. So a separable differential equation can be expressed as the product of a function of x and a product of a function of y, meaning that I've got an equation that's got both x's and y's in them. So, and separable, meaning that we're going to be able to separate them, and you'll see why here in a second, but the operation of multiplication is going to be my key that I'm going to be able to separate. And you'll see if I had addition or subtraction, I would not be able to separate. So this is an example of a separable differential equation. So it's a derivative, but in order for me to then anti-derive it, I can't use substitution because I've got this y term in there. Now, first of all, let's acknowledge where this y term would have come from. Well, remember, when we do implicit differentiation, that gives me dx's and dy's, and I could have a whole mix jumbled up of x's and y's. So it's possible to get derivatives that are in terms of x's and y's. Well, now I kind of want to undo that. So what I want to do is I want to separate the variables. So I want to multiply and get the x and dx on one side and the y's and the dy on the other side. So we're going to multiply by dx and divide both sides by y squared to separate these variables. So I'm going to actually break up this Leibniz notation and use these little differentials. So keep the x's typically on the right, because we usually like to write equations y equals in terms of x's, and the y's on the left. Notice I didn't bring the 2 along. Again, the more terms that you bring over to the left in terms of y, the more terms eventually you're going to have to move back over, because eventually we will like to solve these equations for y. So now that I've separated, and I can just rewrite this as y to the negative 2 dy and 2x dx. You should be doing this with me. Well, now what I can do is I'm ready to integrate both sides separately. So I've separated the variables into x's and y's, so now I can perform my anti-differentiation on both sides. So power rule on the left with the constant added in, and a power rule on the right with a second constant added. So I've got 2 different constants going on here, but we will combine the constants together into one giant constant of integration. And typically we'll put that on the right side, because ultimately we're going to try to solve these equations for y, get the y by itself. So you might quickly, and you'll see me, get into a habit of just writing the plus c on the right side. Doesn't mean that there wasn't one on the left, but we're combining them together. So in negative 1, y to the negative first is the same as negative 1 over y. And now to solve, I will reciprocate and negate both sides. And so I get an expression that's like this when I solve for y. So again, what I've got is I've got a function whose derivative now, if I took the derivative, would give me 2xy squared. Now, when you might say, well, that doesn't have any y's in it. Well, remember, I could then, after I took the derivative, rewrite my original expression, or sorry, my derivative, my differential equation, with substituting that y, newly found y expression in, and we should get the same thing. All right, so let's take a look at another one here. So I know I've got a mix of x's and y's, so I'm definitely going to have to separate variables here, separable differential equations here. So let's jot that down. If you want to pause me and try to get the y's on one side and the x's on the other side, go ahead and do that. So I can just divide that whole term over to the left, keeping the 2x e to the x squared on the right, which now means I'm ready to integrate. So let's kind of scan what's going on over here. Over there on the left, 1 over 1 plus y squared. Do we know what function has a derivative of 1 over 1 plus y squared? I hope we do. I hope we see that that's an inverse tangent. Yeah, we're going to have to remember all of these. And what's going on there on the right? Well, I've got e to the x squared and then a 2x. I hope with all of our practice of integration by u substitution, we can almost look at this as e to the u du. But let's spell it out. So I'm going to let u be x squared. That's the function that's sitting inside the e to the x function. Obviously, its du is 2x dx, which I have. So therefore, I can rewrite this integral on the right side as e to the u du. Notice I didn't differentiate on the left. I kind of saved that all as one step all together, which happens here. There's my inverse tangent. Constant on the left, constant on the right. Hey, don't forget to put the u back in. So now everything's in terms of x's and y's. I don't want a u. And then we'll combine into one positive c or plus c on the right side. We're going to combine them together. And now my task is just to get the y by itself. So here I am. And hopefully you remember from Mrs. Miller how to undo an inverse tangent is we can take the tangent of both sides, because the tangent of the inverse tangent will just cancel out and give me y. And there's my solution. And again, remind yourself of what we're doing here. I've got a derivative, and I'm trying to figure out what was the original function that had that derivative, and it is this function. Or I should say these functions, because of the extra plus c. It's an infinite number of antiderivatives here. All right, and again, very systematic method that we're going to do here. So let's talk about what would happen if I wanted to actually solve for c. Well, I've got two examples here, so let's take a look at those two examples. I'm going to actually do them here. So here's my first one. So I don't know, at this point, maybe if you can go ahead and pause and maybe get it to the point where you can then solve or get to the point of anti-deriving. Once you anti-derive, don't solve for y yet, but just anti-derive and then stop there. And then you can turn me back on. So I'm gonna separate my variables. And then at this point, I know earlier I was doing it as an extra line, but now I can just introduce my integral symbol here. Okay, obviously on the right-hand side, that's going to be easy. That's going to be x squared, and I'm going to put my plus c on this side. And over here on the left, what function has a derivative of 1 over y? Well, that's the ln of y. And remember, we're going to have to put in absolute values here. And we'll talk about that here. And you'll see it here in a second, because here's my biggest suggestion for these initial value problems, where they give you a value that you'd like to pass through. You want to immediately after you anti-differentiate, solve for c. Don't start solving for y just yet. Solve for c immediately first. So I'll put in my y value and my x value. And first of all, now you can see why I need the absolute value. I can't take the absolute, the natural log of -1. The ln function, y equals ln of x, looks like this. The ln of 1 is 0. But I need to include -1s, so that's why the graph of the ln of the absolute value looks like this, asymptotic at x equals 0. So ln of -1 is still going to be 0. Absolute value of -1, I should say, is 0, equals 1 plus c. So I see c is -1. So I'm going to go back to my step here. ln of the absolute value of y equals x squared minus 1. So now I want to solve for y. Typically on the AP exams, they ask you to solve for y equals f of x. Solve explicitly for y. So how do I do that? Well, I do it the inverse of the natural log function. So I take e to both of those powers. Left side, I get absolute value of y. Right side, I get this. Now I still have this absolute value here, which really means that this expression on the right could either be positive or it could be negative. Now it can't be both, so what I have to do is to check how it satisfies that initial condition. My initial condition was 1, -1. When I put 1 into this equation, I better get -1. Well, if I put 1 into here, 1 squared minus 1, that's 0. E to the 0 is 1, but I need to return -1. So my solution for this particular initial value needs to be that equation with the negative. So is it possible that there are other solutions that pass through other points where it's going to be positive? Absolutely. Absolutely, especially if this just wasn't a negative number. If it was a positive number, well, then I don't need this negative. I don't just leave it as positive or no sign there altogether. In the end, these initial value problems, the best thing that you can do is in the end, make sure that you substitute in and you get the solution, whether or not it needs a plus or minus, but just checking it as a solution. Again, so 2 hints: solve for C right away and make sure you check your initial condition once you've solved for your explicit antiderivative or solution. All right, let's do one more here. So again, pause me now if you want to actually take it all the way through. So separate your variables, integrate, solve for C right away, and then solve for the explicit equation y equals. So first of all, I have that expression. And then getting my y's on one side and my x's on the other side. And now I'm ready to integrate. Oops. Obviously, this side is 1/3 x cubed plus c. And this side, be careful. Some of you might want to say ln of y squared. Nope, 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 nope. That's only when I have 1 over y to the first. This expression is really y to the negative second. So I need a power rule. So I get this. I'm just going to rewrite this. I'm not solving anything, but just so I can see it a little bit easier. All right, no rearranging. Don't do anything yet. Let's actually put in my initial condition and solve. So y is 1, so that's going to be -1. 1 cubed is 1/3. So it looks like I get c is -4/3. So I go back up. I'm going to go to this version right here. So I get -1 over y equals 1/3 x cubed minus 4/3. So this technically is the solution, but again, we like to solve for y when we can. And we're going to do that here. So what can I do? Well, first I can take that negative over to the other side. And so signs change. And then the nice thing you can do here is I would just like to reciprocate this left side, which means I got to reciprocate the entire right side, not just the individual terms. This is an acceptable answer on the AP exam. You don't need to simplify, but you can see if this is multiple choice, I want to make sure that you can see what this solution would look like. These do have a common denominator here, and then I can multiply by the reciprocal. Probably if this was a multiple choice problem, it might look something like this. Again, this is acceptable if you were just doing an open-ended question, but multiple choice answers could look like this, or even possibly like that. All right, so separable differential equations separate the variables, antiderive. Initial value problems require you to solve for a C. And again, oh, let's do what exactly I said in the end. Let's just make sure my initial condition works. Let's put 1, 1 into here. So at 1, 1, I get -3 over 1 cubed minus 1. So that's -3, and there we go. I get my -1, which is what I wanted. All right, time to practice. All right, do well, guys, here.